Hi everyone, today I would like to talk about multi-objective least square. In the last video, I talked about the least square. I talked about the normal equation, how to find the solution to the least square. Now this is the extension to the least square problem. That in a sense, instead of optimizing or minimizing one cost function, in the multi-objective case, we are trying to minimize or make multiple cost functions small. What's the problem formulation? Here, we are trying to find the x, this x, such that it makes multiple cost function small. Now, if each of these cost function are in the form of least square, then we call it multi-objective least square problem. Let's see what I mean. So remember in a normal least square or ordinary least square, OLS sometimes called, we are trying to minimize this quantity for x. This is for OLS, ordinary least square. Now in a multi-objective least square, we are trying to find again one x. So let me just write it by as a lowercase x. That is a vector. We are trying to find one x, right? Same x. That makes J1, J2, these are different cost function, different least square problem small. So in a like OLS, we find one x that minimizes this cost function. Now here, you have an x that maybe if the x minimizes J1, make this one, let's say, 0. For example, let's say it's the solution of x equal to b. But maybe makes this one 10, make this one, I don't know, 15. And maybe that's one solution. Maybe there is another x that make this one 0, right? Another candidate that makes this one 10, make this one 20, for example. Or we have k of them. But we are looking, maybe there is an x that doesn't make any of them 0, but make this one 1, make this one 1, and make this one 1. We are looking for that x, right? That make all of them collectively small. Okay. So now that we understand what we are trying to do, in general, for this J1, J2, Jk, the vector B1, B2, and Bk are different, and the matrices A1, A2, also Ak also different. So to be exact, this should be like A1, this should be A2, and this should be Ak. And the dimension of that, as I wrote here, AI is Mi by n. So Mi row and n columns, and Bi is Mi by 1. What I mean by that, for example, A1 is M1 by n, A2 is M2 by n, right? So they don't have to have the same number of rows, but they should have the same number of columns. Why is that? Because there is only one x, right? So when you multiply A1 by x, the number of columns of A should match the number of rows of x. So x should be n-dimensional. Therefore, each of these A's, A1, A2, all the way to AK, should have n number of columns. Okay, so now we know what we are doing in the multi-objective least square. So as I wrote here, we have k different least square, but we are trying to looking for one x, a single x, right? That makes all of them small. Okay, so one way that people formulate, one very famous way or well-known way that people use to formulate the multi-objective least square is to find them or minimize the weighted sum of all these least square problems, all these j cost function, right? Why is that better? Because here, how would you write it? You're gonna write what? You're gonna write mean of j1, j2, all the way to jk, right? It's not really that easy what we are trying to do here. One way to formulate this is to write, I'm trying to minimize the lambda 1 j1 plus lambda 2 j2 all the way to lambda k jk, right? So weigh the sum of these cost functions, where lambdas are the weights, right? How much weight you put on each cost function, how much each cost function is important for you. Now each j is of course a least square problem, so we write it as a least square problem, and this is the total cost function that we are trying to minimize. Okay, and lambdas, the weights are all non-negative, or they are all positive actually, right? So we restrict them not to be 0 as well. All right, so now that we know that we have one cost function for this multi-objective problem. The goal is to solve it. How can we solve this problem now? There are two ways you can solve it. One is just by direct differentiation with respect to x, right? Like the way we solve the normal list square problem and set it equal to 0. Two is using this idea of a stack matrix, right? Which these two methods are pretty much the same, but one of them is a shortcut, like this stack matrix. Let's take a look at this. You see, I want to formulate this multi-objective problem as similar to the OLS, similar to ordinary list square. Okay, so that's the idea behind this stack matrix. You see, we had a property of a norm. I remind you, here, remember we have a norm of lambda times a, where a is let's say lambda times x here, where x is a vector and lambda is a scalar. And if lambda is positive already, this is going to be lambda times norm of x. If lambda is not necessarily positive, you would say the absolute value of lambda, right? Okay, good. Now, if you have some sort of this lambda times x squared, what's going to happen here? We're going to have lambda squared times norm of x squared. Okay, good. So in a sense is that since lambda is a scalar, you can take it out of the norm operation, right? So the idea behind the stack list square is as follows, right? You see, we have this lambda 1 here in one of this cost function. Let me just write it here to explain it better. Let's consider one of this cost function. We have lambda 1 norm of ax1 minus b1 squared. In a sense, I can write this one like that as well, right? I can write it square root of lambda 1 times ax minus b1 square, right? Norm square. This is the same thing as I just explained. Because when you square that, you can this square root of lambda 1 is a scalar. You can take it out of the norm, but you have to square it first. So you get lambda 1 times norm of ax1 minus b1 square. Okay? So the same thing is here. Now, what we are going to do, if I want to explain further with this, we get lambda 1 ax1 minus lambda 1 b1, right? So you see that I can write it like this. I can write it as 1 list square problem. But now that we have different a's, in a sense that my a new a is gonna be this. Round up and square root of lambda 1 times a, and the b is gonna be a square root of lambda 1 times b1. Okay, so this is the idea. We're gonna do the same things for different cost function. In that case, we will have a new a, which the new a will be this, right? So it's gonna be a square root of lambda 1 times a1 all the way to a square root of lambda k times ak. Okay, so let's call this one, I have it here, I call it a bar. Now I call this one as again b bar. So if you look at this is similar to OLS, ordinary list square problem, right? But we already know how to solve this problem. So this is gonna be like this: norm of ax, a bar x minus b bar squared. But this is like OLS. So the solution to that is nothing but this normal equation, right? Remember, I explained that this is like a pseudo inverse. Right? Okay, so that's gonna be the solution. And then, of course, we can write it in terms of equivalent of A1, A2 all the way to AK, and B1, B2 to BK as well. So just something, this should be B1 as well. Okay, good. And then, of course, we can write the equivalent as well. A bar transpose is gonna be this, and then this is gonna be A bar, and this is gonna be A bar transpose times B bar. Okay, good. So this is the idea that we have here. So this solution is definitely valid, what we have here, this solution. Now, One thing that is very interesting is to ask ourselves under what case we can even write this solution. Under what case, let's call it equation one. This equation one is even valid, right? I recall, let's remind you something that when you have when you're trying to solve a least square problem, like this minimum of ax minus b square, the solution, of course, was according to this normal equation a transpose a transpose b. We defined this one, it was a pseudo inverse. What for what? For left invertible matrices. So we consider A to be tall or square. So we considered A had to be tall or square with linearly independent columns. Linearly independent columns. Okay, so the same idea applies here. If you're trying to solve this stack matrix using normal and using the ordinary, like similar to ordinary least square problem, you should make the same assumption that this A bar, this one, should have linearly independent columns. Okay, and that's what we're going to talk about that right now. So independent columns of a stack matrix, right? So that's what we should now talk about that. So the idea is that to solve the least square problem, to solve the stack matrix as a form of ordinary least square problem, we need to assume that the stack matrix, A bar, has a linearly independent columns. How do we prove this one? We have a standard way to prove this. We say that this A tilde or A bar times x equal to 0. If it has a linearly independent columns, then x equal to 0 is the only solution. Okay, now let's see under what cases this is possible. If at least one of these matrices, A1, A2, all the way to HA, has linearly independent columns, then this A tilde or A bar has linearly independent columns, right? It's easy to see this. Let me show that here, right? So since we are stack them, let's say that A bar is this 1, 2, 3, 4, 5, 6, 7, 8, 9. It has a linear independent columns, right? Then let's say A2 is this 1, 1, 1, 1, 1, 1, 1, 1, 1. All three columns are linearly dependent. But still this matrix has a linearly independent columns. Why is that? Because the column is not only 1, 1, 1. The column is 1, 4, 7, 1, 1, 1, 2, 5, 8, 1, 1, 1, 3, 6, 9, 1, 1, 1. So thanks to the first three columns, or thanks to the first three rows, right? These doesn't matter what are the other rows or what are the other elements here, we always have a linearly independent columns. So if at least one of these matrices, A1, A2 to HA, has linearly independent columns, then this A tilde or A bar has linearly independent columns. Okay. But this stack matrix, I want to tell you something interesting. This stack matrix A tilde or A bar can have linearly independent columns even if none of these A2, A1, A2 all the way to AK matrices have linearly independent columns. That's very interesting. Meaning that if all of them have linearly dependent columns, still the matrix A tilde or A bar can have linearly independent columns. That's interesting. Let's take a look at that. And that's what I'm actually talking about that right now. I'm saying that if none of the matrices have linearly independent columns, still the stack matrix can have linearly independent columns. Okay. Under what case this is even possible? If you consider each of these matrices, A1, A2, all the way to AK, each of them is a void matrix. So we know that void matrices always have linearly dependent columns, right? So what's the example of void matrix? Let me remind you. 1, 2, 3, 4, 5, 6. So we have three vectors in two-dimensional space. Okay, we know that the basis, the number of bases is unique. We need only 2 vectors for 2-dimensional space. So one of them is definitely redundant. So this has a linearly dependent columns, right? Okay. Under what we have a linearly dependent columns, or we have a white matrix when the number of columns is more than the number of rows. Okay. So assume each AI, we had this to be mi by n. Now we want each matrix to be wide. Therefore, mi should be less than n. The number of rows should be less than number of columns. Look at this. Look at this. Here the number of rows is 2, number of columns is 3. So 2 less than 3. Okay. So all the matrices are wide. But then consider the sum of the rows of this stack matrix. What was this stack matrix? The lambda one is not important, but this A1, lambda 2, A2, all the way to lambda K, AK. So what is the sum of the rows? What is the number of rows of this stack matrix? It's going to be M1 plus M2 all the way to MK. Now, if this M1 plus M2 all the way to MK is greater or equal to N, then we will have a tall or square matrix, right? Then A tilde or A bar is going to be tall or a square matrix. Then it can have a linearly independent columns. So if none of these matrices, A1, A2, AK, if none of them has any linearly independent columns, still the A tilde matrix can have linearly independent columns, right? As long as the sum of the rows of each matrix, when you sum the sum of the rows, right, M1 plus M2 and MK is greater than the number of columns of this A tilde. Okay, that's very interesting thing to know. Now let's talk about something interesting. It's called regularized inversion or Tikhonov regularization. It's very important in literature, optimization literature. Tikhonov was the name of person that came up with this idea. So what's the idea here? What's the problem? We are trying to minimize the least square problem, multi-objective least square, that one of them this ax minus y square, right? This is like J1. The second objective is like a norm of x square, right? When do we use this type of formulation? When do we use that? When this A doesn't have a linearly independent columns, or this A, we usually say that is not well defined, right? We use this type of formulation. Or the most important application of Tikhonov regularization is that you want to minimize this least square, this problem. However, you don't want the norm of x to be too big. You want the norm of x to be small. You want x to be a smaller values, right? You will add that one as a type of objective function as well, right? So remember, when egg does not have a linearly independent columns, you will add some sort of regularization, right? Because if A doesn't have a linearly independent columns, we proved this in the previous videos, then A transpose A is not invertible. So you cannot calculate this. You will see how when we solve this Tikhonov regularization, you will see that how we can actually overcome this problem. Or we want to minimize this quantity, but we want the norm of x to be as small as well. So we add it as a form of objective to our problem. So there are two ways to solve them. They are kind of similar, as I motivated that before. There are two ways to solve this multi-objective problem. Let's go through both of these methods. Method one, using a stack matrix idea. Okay, so what is this problem we are trying to solve? Is actually we want to minimize the norm of ax minus y. So here the first a is a itself, but then the second one, so think of this one is again as a least square problem. But the difference is that you can write this one like this: I times x minus 0 square. So b is 0, and then a2 is I, and b2 is 0. Okay, so this is gonna be a, because there is no lambda here, and the second one is gonna be the square root of lambda times I, because the a2 was I. And so this is y bar, you can call it b bar, doesn't matter. It's gonna be y is for this one, and 0 is for the second objective because the b value was 0. Okay, now we can write it like this, and after that we are done. Why is that we are done? Because we're gonna write it as a solution to the normal equation. That's the famous solution that we had for the least square problem. Before that, let's check something very important. In order to use this one, we need to prove that this A bar has a linearly independent columns. How do we prove this? Let A bar times X equal to 0, right? If A bar times X is equal to 0, I will write that here. It means this, equal to 0. This means that AX equal to 0 and lambda I, square root of lambda I, X equal to 0. Okay, but wait, this is gonna be, I will write it in one shot here, right? So this means that X is equal to 0 from here, from the second equal constraint that we have. This means that X is equal to 0. Therefore, A tilde X is equal to 0. It gives us X equal to 0. So we know A tilde has a linearly independent columns. Okay, good. And therefore, the solution is nothing but this expression. Okay, good. And then you can go ahead and write it based on this format as well. Right, so this is going to be A tilde transpose based on A and lambda. If you go ahead and simplify this, you get to this very famous equation. You see, it's very similar to the least square, to the OLS. What with the difference is that we have this lambda I now. So if A transpose A is not invertible, you see what we are doing. We are adding this regularization. This lambda is called regularization factor. We are adding this regularization, right? So lambda times I is a matrix as well. We are adding this in such a way that A transpose A is invertible. Okay, great. Now let's go ahead over method 2. So remember, this is a very famous equation. Method 2. Method 2 is the same thing. Instead of going through this stack matrix formulation, we're gonna forget about all this. We're gonna write the norm of x square like as x transpose times x, and norm of ax minus y square as ax minus y transpose times ax minus y. The same idea. Write them together, simplify, take a derivative with respect to x, set it to 0, and find the solution. Right? Assume we didn't know about anything about this stack matrices. So you're gonna write it like this. This is norm of ax minus y square. This is lambda times norm of x square. You're gonna simplify this, write it like this, multiply them and simplify that, and then take a derivative with j respect to x. You get this, right? And then from here, x bar is gonna be equal to, or x hat is gonna be equal to A transpose A plus lambda I inverse A transpose Y. The same solution, right? So idea is this formulation, the solution is slightly different, but the answer is exactly the same. Okay, so again, A transpose A might not be invertible by default. You add this small perturbation to make sure that now it's invertible and the solution makes sense. Okay, so that's it for this video. In the next video, I'm going to talk about the constrained least square, which is very, very important class of least square problems. Thank you so much for watching.